As usual, review what we did last time. And unfortunately, of all days, today's a brutal lecture. Today's a Carnot cycle. We're going to calculate the efficiency of a car engine, or of any engine. We think that the equation that I'm about to derive for you is applicable to anything. Car engine, power plant, rocket engine. And it all starts with the idea of a reciprocating engine. I hope I've drawn that okay, maybe a little bit better than yesterday. And of course, you know, we want to turn a crankshaft. And that turns the wheels of our car, it would turn the turbine of a power plant. I'm not quite sure how I could relate that to a rocket engine, but that would pretty much cover all our bases. Okay, versus a wind-up spring, which is ridiculous. No one's going to build a wind-up spring and drive anything on that. So anyway, all right, so Carnot, 18-something, young guy, cannoneer, he is trying to figure out, he knows that he wants a reciprocating engine. He knows that any modern tool is going to work this way. And he's probably thinking mostly of steam engines. We can't really know what he's thinking because, you know, he's dead. But that's probably, you know, they were building steam locomotives like mad because they just basically invented them. They were insanely useful because other than that, you're on a horse, right? And seriously, that's all they had. So what he knows is that, okay, we're going to turn a crankshaft, and we're probably going to do it with an expanding gas. And I'm still repeating what I did last time. So we're going to expand the gas volume. And that is our power stroke. So now again, we've got to be real practical. And you saw in the exam as well how I expected you to know things like you know, a lot of you missed this. If you compress a gas, it naturally gets hot. About a quarter of you said cold. Well, come on, you should know that that's not right. So again, we're very practical in this class. Carnot knew that. Remember, I drew that picture of an engine in the textbook, or I talked about it last time. Carnot knew that if you're going to really turn the wheels of something, of a steam locomotive, that's what he was thinking of, that it's going to be a push, right? There's going to be, like, in his case, hot steam, or in our case, burning gas. In a car engine, it's going to be a push, right? And that's going to be work out, right? Because otherwise, you know, it's easy to burn gas, and then, of course, the piston expands, and that turns the crankshaft. That's called the power stroke. How would you generate a reaction? How would you have a reaction that generates a vacuum, right, suddenly, and then pulls? You could, it just, not really, no, that's not going to work. So he knows that he wants to push, and that's correct. Okay, so we expand the gas, and that's our power stroke, and there you go. The problem is that you got to return, right, so there's our power stroke, but you got to go back in a circle. And that introduces a hideous problem. Now you got this right, I'm still reviewing. If you're going to go backward, then the area, which is the work under the curve, now I've offset these, and you know this, I'm again still reviewing from last time. The forward and backward work are equal, plus minus. They're equal, so the net work would be the work of the expansion and contraction, I won't write that, is 0. Now, practically, again, we're being practical in this class. What that means, it means that you get the power stroke, but on the way down, before it goes back to the starting point, it would actually stop. So it's the engine that stalls, so that's not going to work. So Carnot's idea was, now this is, I have to admit, this is really clever how he did this. He figured out what you want to do is drop the temperature. And then you go back. Okay, so now here's the backward work, and here's the forward work. The negative work, the pushing work. And he realizes that the expansion produces more net negative work than the contraction, which is positive work, right? You and I had to think about it. And that you would generate a net negative. So that would be less than 0. Make sure to keep it straight. Okay, now he ran into the problem of how do you actually do that. Now the funniest thing was historically, it turns out that the people designing steam locomotives were obviously, like engineers, they were tweaking the engines and they were accidentally discovering these thermodynamic principles. People like Carnot were looking at these guys, what they were doing, and doing it on paper, but they actually never spoke to each other. And it turns out like around 1900, when the locomotive engineers started realizing that thermodynamicists were describing locomotives, they realized that they had basically built it optimal conditions, but they never actually spoke to each other. Anyway, that's kind of neat that happened. Okay, anyway, kind of a big fan of history. Okay, now here's where Carnot then again does something else that, you know, if the guy lived and they had a Nobel Prize in 1880, they didn't. But if he lived and they had a Nobel Prize, he absolutely would have won it for the stupidest thing imaginable. So again, how do you do this? How do you do this, and how do you figure anything out from it? And you may recall, those of you looking in the book, that I had this picture in there. And this is a famous picture. Carnot actually did draw this. He did have some surviving records of, again, I'm drawing the magic piston, hopefully getting it right. I did draw all those figures in the book. Am I drawing? Yeah, I'm drawing that right. So what he did was he said, I'm going to put a piston. Now notice that it's enclosed. And let me see if I can communicate its 3D look. There you go. Okay, so he creates a piston and he puts it on a hot block. All right, now what happens is, of course, the gas in here, let's make it enclosed, as dangerous as that is, the gas in here will get hot, and that means that the piston's going to push up. There's our power stroke. There's the work out, and it's hot, so we're expanding hot. Then what the guy does is says, well, okay, I'm going to take that same object, and I have to look at this, make sure I don't screw this up. I'm going to take the same object, now expanded. Now it's expanded. And, of course, what he does is he puts it on a cold block. There we go. I'll do that a little bit better because I'm practiced. There we go. Okay, now it's sitting on a cold block. And, of course, if it's cold, then what happens is the piston contracts. So, there we go now. Let me draw that here so you can see it a little bit better. There we go. Okay, so again, the whole idea is expand hot, contract cold. And then he just drew this really simple picture of an enclosed volume with a little piston head, and of course it expands when it's hot, and then to get it to go back to its original state, he puts it on a cold block. Now you know this would work. This is like the world's worst child's toy. But the thing that's incredible about this, it allows him to apply thermodynamic calculations to this and figure out all kinds of stuff which we're about to do. And he nailed it. So Carnot, because of this very simple drawing, what it does is it allows you to analyze it. It allows you to analyze a reciprocating engine. Because of this, and he basically figured out what entropy was. He didn't give it a name. That almost all thermodynamics is attributed to him. He's considered the alpha and omega of all thermodynamics just to think of analyzing a thing this way. You know, like Einstein. Einstein never did experiments. He just thought of things. Like, how should this work? E equals mc squared comes about from, I shouldn't be talking about this, I know, but I'm in a spaceship, you're in a spaceship, and you're moving towards a star, but I'm not. Yet we measure the same speed of light. And that's where he gets mc squared, by the way. He didn't actually do it, obviously. And so Carnot does the same thing with this. All right, now this gets painful, folks. I told you that this is an incredibly painful lecture. This is it. We have to draw the Carnot cycle. So what we're going to do is take this and we're going to expand it hideously. And then we're going to do two incredibly long derivations. I often get this wrong, by the way. I'm going to try my best. There's just a lot to this. Okay, now notice that I've gotten a very, very big graph. So you might want to get a piece of paper and turn it on its side, by the way. We're going to start at P1, V1, T hot. Okay, so it's a magic piston. It's the Carnot piston. Start at point 1, not too difficult. The thing to remember is that it's hot. Now what happens is there's going to be a heat injection. Now, analogous to an actual car engine, or maybe let's do a steam locomotive, that's the injection of steam. Car engine, the spark plug fires and you burn gas. Okay, so there's our expansion. And we're going to make that isothermal and reversible because why the heck not? We want it to stay hot. Remember I said expand hot. So we're going to make it isothermal. We're going to make it reversible because we want negative work. And remember, this is all in our head anyway. It's all theoretical. We want the most negative work. We want it isothermal to expand hot, so therefore we make it isothermal and reversible. So let me write that down. So this is, you may have a hard time seeing this because I have to write really small because I'm going to have to write a ton of stuff. This is, again, bloody awful. If you have trouble seeing, watch the video, read the textbook. I think the textbook is okay. This is about to get much worse. Okay, so then we're at P2, V2, T hot. Okay, now this is where Carnot does something that's really clever. Contract cold, but instead of just dropping straight down, which is kind of like, how do you really do that? Well, I guess you could maybe do what I just draw and put the magic cylinder on a cold block. But Carnot knows that there's another way to cool a gas. What do you think it is? Increase the volume, but under what conditions? Now hold on. I just increased the volume, but I kept the temperature hot because it's isothermal. Adiabat, right. Follow an adiabat. Adiabatic expansion. And of course we're going to make it reversible. Right, so this is where Carnot is really clever. He figured out that, so this is kind of funny. The reason that a lot of other people are trying to do this, but they didn't get it quite right, because what Carnot did, and again, this is all magical, right? It's all magical. He says, I'm going to do isothermal expansion, but then I'm going to suddenly wrap it in glass wool so that the temperature will drop, and then I'm at my cold temperature, and then I'll let it contract back to complete the cycle. Expand hot, contract cold. This is how it gets to the cold. Okay, so now we're at P3, V3, but now we're at a lower temperature, colder temperature. The point of this is that he got a little bit more work, right? You see how clever that is? He got some more work out of it by letting it expand. So there's a little more push to it. And this was really clever of him. Okay, now you can imagine that then, because we're going to contract cold, we're going to do isothermal. And I never quite get this right. We're going to do an isothermal, reversible contraction. Now at this point we're just trying to get to state 1. And then of course we have to get it hot again, so the last leg will be adiabatic reversible contraction so that we jack the temperature up. Of course we're going to be at P4, V4, T cold here. Okay, not too painful, but now what I have to do, this is the part you don't like, I have to start inserting all the equations for heat and work. So this is where this gets kind of hairy. And I think I can already tell I don't have enough room, so this is going to kind of blow. Okay, so here, let me, I hate doing this, but anyway, a little line here, right? So you see what I'm doing. Now here's something that's a little funky. Let me start with work, and I'll call that the first work. And no. What am I? I'm going to go ahead and integrate it. I'm going to go ahead and integrate it. So remember, folks, I am kind of careful about the little d is a partial, big D, big group D is integrated, because a lot of you didn't integrate that question on it anyway. Said I wouldn't talk about it anyway. Okay, so let's integrate the first work, and it's just a reversible isothermal. Of course, the temperature is hot. N is constant, R is constant. And of course, the final volume is V2, the initial volume is V1. There you go. Now this is, part of this is a little bit funky here. Now remember that we start with a heat injection, so I'm kind of tempted to start out with, here's the heat and then describe work. But at the same time, you're kind of more in tune with work. Work is a little bit more easy for you to understand, so I'm starting with work. But just remember that heat is what comes first. But just notice that I've written minus the heat. So just be a little, it's not a big deal, but just be a little wary of that. Okay, so I've described the work and heat, and now I have to look at my notes. And so, okay, so I've done the first leg. Second leg. Second leg, this one's a little bit easier. What's the heat? 0. What is it? It's adiabatic?
0.
Right, always write 0. That'll be on the second test. Second test is going to be the magic piston expands, contracts. What's heat? What's work? What's S? What's U? What's H? What's G? What's A? What's CP? What's B? What's... I told you there's 12 of these, right? Okay, if it's adiabatic, you write dq equals 0 immediately. Okay, the work. The work is easy CV delta T. And of course, that's going to be the final temperature is T cold minus T hot. And that, I always want to write it the reverse because I always want to say the final temperature is hot and the first one's cold, but no, I just have to pay attention to what I'm doing. That's the hard part. Okay, now, next leg. So I'm going to write that all here. I barely have enough room. Okay, this is the third, minus NR. Pretty simple. The temperature is now cold, and the final volume is V4, and the initial volume is V3. Sorry, that looks messed up. It's just, I'm writing badly because I'm cramped and oh God, this is bloody awful already. All right, but fortunately we're almost done. Okay, last leg, and I'm going to have to just write it out here. The heat. Okay, that's easy. Actually, this isn't so bad. And the work in the fourth leg is just CV T hot minus T cold. And that's because it's meant to heat up in the final state. So the final temperature is hot and the initial temperature is cold. Now again, I know this is absolutely painful. It's in the book. I also have a handout, and watch the video if you know, if you had a little trouble with this. Also note that sometimes when you guys come by, not so much you folks, I bet that's going to change. You haven't been coming by office hours, but historically sometimes when students have been having some trouble, I notice your notes aren't right. So that's one of the reasons I wanted to start to do videos. Okay, question?
What about Q3?
What's Q3? Oh, and this is, of course, minus delta Q3. And that's thank you, because that's very important to the entropy. Yeah, everything is, I think I got everything, right? Yeah. Okay. So there you go. Now this isn't the bad part. Now we want to do the work. And here's something that will hopefully be so what we're going to do is calculate the total work. Now hopefully, based on what I just drew, you can see that the negative work, which is the area under the lines on top, to be very crude and plain spoken, the area from the lines on top are greater than the area from the lines on bottom. That's the whole point of this, right? So you can see that we're going to generate a net negative work, but of course this is math class, so I need to prove it. Okay, net negative work. Now this is where I kind of know what trips you up because I can remember being you. And here's what I bet you're going to struggle with. Is this work positive or negative? Okay, and work here? It's an expansion. Negative. This work? Positive. Okay, so do I add up? Wait, or do I subtract the first work and subtract the second work? Or let it be negative? What about the third work? Should I add that or subtract it? Add them, right, add them all. Add them all. I know this is the kind of thing that would get you. You're sitting here thinking like, oh, is it positive or negative? It's negative, I subtract it. If it's positive, no. Energies always add. Now here's what you want to remember. If they're negative, let them be negative on their own. If it's negative, it naturally subtracts. But subtraction is just the addition of something negative. So there you go. Add them up. If they happen to be negative, then they have to be. Then they're subtracting themselves. So that's how you do that. Okay, now it turns out that, oh, holy God. Okay, I resent this right here. Let me put this right here. I'm just rewriting the same thing because I want you to be able to see this while I write this, but this is in my safe zone and it's triggering me. So there we go. Okay, so I'm going to try to keep this here while I do all these derivations there, but this is very, very, very painful. Okay, so the total work is now, and I have to write kind of small, so don't go too nuts on me. Okay, so here is the first one, and here is the second one. Okay, the final is cold. Now I'll have to subtract the third one. I hoped I wouldn't have to do this. No, add. Sorry, add the next one, which just happens to be negative, which is cold. And then maybe I ought to actually look at my notes. Ln V4 over 3, V4 over V3, plus CV, that's going to be T hot minus T cold. Right, now you guys let me know if I'm not doing this right, okay? I know it's a lot to keep up with. This is why this kind of sucks. This is why I need to, see, this is why I have two boards. Normally I put one of these on one board, raise it up, and anyway. Okay, so now I can eliminate two terms. Can you see that?
Yes.
Yeah. You're just trying to make me feel good, or what? Right. That is minus that, right? So there you go. Okay. All right. So now what? Okay. So I am left with this, and this is unfortunately the part you get a little cross-eyed. I can obviously factor out an NR. And I've got the hot temperature ln V2 over V1, and then I'm going to add in the cold one, V4 over V3. Okay. Oh. And I can see I don't have room to finish this, but I'm going to try. Okay, here's the trick. The name of the game is that I'm trying to get to the total work, but I just want to simplify this as much as possible. The reason is that I'm going to need the work, I'm going to use the work to calculate the efficiency. That's my ultimate goal. Again, I have this equation for work. I'm technically done. I was technically done when I was up here. I just don't get a lot out of it right now. I want to simplify it further. And for one, then you're going to be able to tell easier that it's net negative. The second thing is I'm going to be able to use it in the calculation of efficiency. Question?
You're missing a natural log.
Yes. Yes, I am. That's why I was perturbed. Thank you. Ln V4 over V3. Thank you. There you go. Okay. Now here's the trick. Again, we're trying to simplify it. And it's the natural logs. It's the natural logs I'm going to be able to put together. Now the trick is going to be that in the adiabatic transitions, V2 and V3 are connected in the second leg, and V1 and V4 are connected in the fourth leg, the adiabats. So again, my trick here is to connect V2 to V3 and V1 to V4. And if I establish a relationship with them, I'm going to be able to factor those natural logs. I'm going to get a much easier to digest formula for work that will also be useful for the future. Okay. Now again, you know, I told you I try not to do this, but here we are. And I'm going to have to write this down, and I'm going to have to erase it because I'm running out of room. Okay, I am just writing the adiabatic equation of state, the volume and temperature form. You know that there's a couple of these. So VI over VF, the initial volume, again, we're doing the second leg adiabat, VI, VF, so I did VI over VF is TF over TI, the final temperature is cold, and the initial temperature is hot. And that's to the CV over NR. Okay, there's that. And I happen to know that V4 over V1, final initial, is equal to initial final. The initial is the hot one. No, initial, final, initial. Right. The final step in the fourth leg is the hot. T cold CV over NR. Okay, so here's the thing. Cold, hot, hot, cold. And I've got 2 connected to 3 and 1 to 4, right? That's the whole point. Okay, now what I can see from here is that V4 over V1 is therefore equal to V2, is that right? V3 over V2? Okay, so I'm kind of out of room normally I write this out a little further, I do some algebra, but can you see that? This is the inverse of that. You follow me here? This is the inverse of that, so therefore V4 over V1 is V3 over V2. This. No one's having any trouble? Yeah, I see a lot of heads shaking, so okay, so I hope so. Okay, therefore, okay, V4 over V3, what I'm doing is I brought this down here, V4 over V3, so I just scooted this over here, so therefore I better scoot the V1 then better take V3 spot, and V2 is still where it's at. There we go. Algebra, just algebra. V4 over V3 is V1 over V2. Okay, so now what I want to do. Oh God, I'm actually almost there. All right, now now I have to erase this. I have to erase this. I'm out of room. Okay, so I hope you followed along. I'm going to leave this equation for work on top. Wait, sorry. I told you. Watch the video. That's why I have videos. That's why I have a textbook. Okay, that's what I figured out. I'll leave this. Okay, so the total work is minus NR T hot Ln. I'll leave this one. And I'm going to go ahead and subtract T cold. Okay, now again, be careful. Be careful. I've done 2 steps again because this freaking board is too small. Hold them and put me in a different room. All right, you see what I did? I substituted V1 over V2, but I made it V2 over V1 by putting a negative sign. Natural logs. ln A over B is minus ln B over A. All right, you should know that. That's one hopefully you got in high school, and you should be able to carry that with you. Anyway, so it seems like magic because I used an identity. Okay, now let me erase this because I'm almost done. Again, I'm just trying to simplify this so that the result is more clear. Okay. Now what have I got? I got minus NR, I'm going to leave that. ln V2. What's good about that is I know that ln V2 over V1 is positive. And then I've got T hot minus T cold. And that's squished, but it doesn't look too squished. Hopefully I manipulated the board. I'm kind of getting better with this board. So that's it right there. That's the net work. Now, again, this may seem unsatisfying. I'm done. I'm about to do something kind of cool with it. You just don't see it yet. What I do get from this is, all right, is T hot minus T cold, is it positive? Obviously. I just said ln V2 over V1. V2 is bigger than V1, positive. R is positive, N is positive. Minus a bunch of positive numbers, negative. Network is negative. Right, network is negative. Now again, on an exam, you know I may throw a graph at you because some of you are good with graphs. Not quite so much this crowd, but I'll still put that on there. Obviously I threw a lot of graphs on there. You guys actually didn't. Normally I get about a third of you acing that, and it didn't quite happen. But I'm still going to have graphs on there, but maybe I'll reduce it because you guys maybe aren't such graph people. Which is fine. I mean, I just want to have different questions for people that just think differently. And then you can avoid them if it's not you, right? Anyway, so net negative. Okay, so what? Now that by itself is we're done. But now let me, because I don't have any other choice, erase all this stuff, and then let's do efficiency. Let's do efficiency, and this is kind of funky. This is going to be kind of funky. So the efficiency of the engine. I can't spell efficiency, so I'm going to write, seriously, I can't. My spelling is getting worse as I age. So write efficiency in your best language, because English isn't mine. Okay, so here's the thing. Modern engines work by an injection of, I shouldn't say, modern engines function by an injection of heat that turns into work. Now, up until the 1800s, we always did the opposite. The donkey pulled the plow, but now we got a machine that pulls the donkey. Anyway, so, or the person in the car. So heat gets turned into work. That's what we're trying to calculate. Okay, now I know what the work is. So now you tell me, what's efficiency? What is it? What makes sense to you to call efficiency? Right there.
How well it does it?
Yes, but now give me an equation. Right there.
The work you got out of it divided by the heat you put into it.
Okay. So now here's a little funkiness. Work is negative. So we add an absolute value sign. Don't forget that. You'll lose a minus sign if you forget this. Positive, negative is to humans. Nature doesn't know plus from minus. Nature doesn't know forward from backward, but we do. We don't like the thought of a negative efficiency. It just doesn't make sense. So we arbitrarily add an absolute value sign. By the way, the handout, I have a Carnot Cycle handout because I forgot the absolute value sign the first time I did this class. You may notice that the type is even kind of old. All right, so now here's the thing. Does that sound right? Total heat? Work to heat. Work comes from heat, so divide the work divided by the heat. Now imagine that this ratio is 1. That's totally efficient, right? Now if it's less than 1, that means not all the heat, so the heat would be bigger, and it is the input of heat, right? So the heat would be bigger and less work came out. So this makes sense because I expect it to be 1 or less than 1, and that makes sense with what I would think of as a percent efficiency. But I gave a subtle clue here. So, total heat?
Change it.
Yeah, kind of. Now this is really subtle here. Remember that we burn fuel. And this is the injection of heat. But what is this? What is happening here? This is a heat release. This is the power stroke. This is the gas burn. This is the open tailpipe and expunge. This takes energy. How much energy does it take to let gas come out the tailpipe? Zero. How much energy does it take to fill your tank with gas? $5 a gallon. Costly, free, right? Okay, so it's not the total heat. It's the first leg. Because that's the one that, yeah, give me money. Again, we just let the CO2 out the tailpipe, but the gas itself is not free. Okay, so this is minus NR ln V2 over V1. Sorry for the compression. Okay, and then the efficiency. Oh, so let me get rid of the minus sign. NR ln T hot ln V2 over V1. Okay, do some factoring. That's gone, natural log's gone, and so what I got is T hot. God, I hope I've done this right. Yeah, T hot minus T cold over T hot, which is 1 minus T cold over T hot. There you go. So that is the efficiency of a Carnot engine. Now, this is like hugely important. Now, what we're going to cover next time is that the Carnot cycle, by the way, is the most efficient engine, the most efficient reciprocating engine you could ever build. So that would mean that, what do you think efficiency is? I've given you another word for efficiency. What's the other word? What kind of work am I doing? Irreversible or reversible? Which one's efficient? Okay, now that we know about entropy, what's the definition of reversible? The new definition of reversible with entropy. No entropy generation, but what entropy? There's three. There's exterior, interior, and total. No total entropy generation. No total entropy generation. So what I'm going to show you next time is how much total entropy is generated? 0. That makes this a perfect engine. You cannot do better than this, yet the efficiency can never be perfect. And this is devastating. I mean, it's kind of good to know, but it's kind of like, hey, you have type 2 cancer, right? It's good to know because type 2 is survivable, but remember the cancer part? Right? So this is kind of like that. You can never build a car that's perfectly efficient. Okay, guys, I know you're troubling a bit, but let me point out something. Let me point kind of cool. Why do cars have big tailpipes? Like muscle cars. Why do they have big tailpipes? Do you see a tailpipe in here? Where's the tailpipe? Cold? Okay, if your cold temperature, let's make your cold 0. What's the efficiency of your engine? Is it better to have a colder tailpipe? Right, that's your heat sink. Why do airplanes fly at 30,000 feet? Yes, the temperature is cold. Right, so that's actually why airplanes fly that high. It's an engine efficiency thing. And it all comes from here. Okay, so again, next time we're going to finish Carnot Cycle and do a little